So today I'm happy to present some of our recent work on integral pose regression. Without further ado then. So the task that we're interested in is 2D human pose estimation, and we're focusing on a specific variant, which is this top-down 2D pose estimation. And what this is if you're given an input image like what you see here, you first detect all the people present in the scene. And so you have this bounding box of the localized people, and then you run this through your pose detection network or algorithm before you end up with this form of output. And so we are specifically focusing on this portion of the pose estimation after the person is detected. So this is what's considered top-down pose estimation, in contrast to the bottom-up, where maybe you want to detect all the possible joints of the people present in the scene, and then you try to group things together. But for us, we're interested in this subvariant of 2D human pose estimation. So it's top-down. And there are two popular paradigms for doing this type of top-down pose estimation then. And they're both similar. Actually, there's 3 variants, but we're going to focus on 2 of the more popular ones. And so what happens is you end up with this image with a bounding box around the person already, and then you pass this through some sort of backbone to estimate some image features until you get some heat map output with respect to a specific joint. So that's what we've called encoding here. And then what we're going to refer to as decoding is converting this heat map into the joint coordinate J hat here, as I'm showing here. And then the 2 different variants that we're considering, the first is a detection-based decoding. And the reason why this is considered detection-based is because you want to isolate that specific pixel, which represents the most likely location for that joint. And so the way we would do this is to take an argmax, as we're illustrating here. And a second variant is to go through integral regression. And why this is called integral regression then is because you actually take this heat map output from the encoding stage, you normalize it. So here, I mean, the normalized heat map looks maybe very similar. And then you take an expectation over the resulting probabilities. And so then you get a slightly different J hat. So we're going to call this J hat sub RE instead of DE, where RE stands for the regression case and DE stands for the detection case. So this is in the forwards pass. And to supervise or to learn this then, you either have a ground truth heat map, which is generated from the ground truth joint coordinates. And so this is what's used to supervise the detection-based decoding, detection-based paradigm. And you pass your gradients back through to the backbone until to learn your overall pose estimation network. The other alternative in the case of integral regression is you also have your actual coordinates, the ground truth coordinates, and then you can impose a loss directly on this resulting joint J hat versus the ground truth coordinates. And so here you can then pass the, because all of these operations are differentiable, we can do a backwards pass and pass gradients all along from back to the original backbone. If we look at this a little bit more formally, in the decoding process, in this heat map detection paradigm, we are taking an argmax over all of the locations in your heat map. And because it's an argmax operation, this is non-differentiable. Whereas in the integral regression, we are doing expectation operation, that's what this is here, of the normalized heat map. And to do the normalization, we use a softmax. So this is the expectation operation over the normalized heat map, where the normalization is done via softmax operation. And of course, the nice part, because all of these operations are now differentiable, we can do end-to-end learning. And that's usually one of the so-called benefits of integral regression for doing post-estimation. Because if I do this heat map detection method, it's not differentiable. So I have to synthesize this ground truth heat map to do the supervision, and on top of which, because my error is evaluated on the resulting joint here, this argmax is not differentiable. Actually, there's some people even use some certain heuristics. Instead of taking the simple argmax, they might even take some weighted value of 2 different argmax and so on. And so if we look then at, for instance, the leaderboard of MS COCO for doing human pose estimation, what you observe is that actually on the leaderboard, pretty much all the leading entries, so all the competing, the top methods for doing top-down human pose estimation, these are heat map detection-based methods. Okay. And this then kind of led us to ask this question, well, you know, is heat map detection really better than integral regression? And if so, then why is it better, right? Basically, why does one seem to outperform the other? And what is the underlying cause for this? And so this is what started our whole motivation of this work here. And we first started out by saying, well, let's create a model of this overall heat map, and then we can compare what the differences are between heat map detection versus this integral regression. And so we made some assumptions that because this heat map, it should be representing a likelihood, right? So the likelihood of that specific pixel being a certain joint. And so we make this assumption that you know, if this heat map is, if the network is properly trained, the resulting heat map, the pixels, the support for the pixelized support for a specific joint, it should be fully contained within some area, which we're going to call phi here. And we further assume then that this area of support can be localized, and it's centered on some location mu, and it's contained within this 2s as the boundary. So phi is completely, so all of the support, or let's say all of the significant support for a specific pixel, specific joint, is going to be contained within phi. And then what we do is we estimate the endpoint error, the EPE. This is what's used to evaluate pose estimation. We take an expectation over this. And so here we can do this for heat map detection as well as for integral regression. And I won't run you through the details of the derivation, but what we find is that if we make these certain assumptions, what we can observe is that for some fixed location of a heat map and the size of the overall size, what we can show is that the expected endpoint error for detection should always be higher or equal to regression. And this result is essentially telling us then that if we have the same heat map, regression should always do better than detection. Okay. So is this true in practice now? So we do a comparison, a systematic comparison, and we actually went one step further and break down the data sets into different sub-benchmarks, because we wanted to also investigate, you know, is it really better? And if it's better, in which situations is it going to be better, right? So we created these sub-benchmarks of dividing, for instance, MS COCO into different factors. So here we looked at different factors like the input size of the bounding box. So the resolution of the bounding box, if it's greater than 128 pixels on any of the dimensions, or if it sits in between 96 to 128, even smaller, and so on. The smallest range is from 32 to 64. So we looked at different factors like input size, the number of joints present in the scene, and also the percentage of occlusion of the present joints. And so if you notice here, I've color-coded each of these groupings. It's because we've deemed these then based on the level of difficulty. So from easy all the way to hard. So if the resolution of the input bounding box is fairly high, or most of the joints are already fully present in the scene, or there's so here, don't confuse the occlusion with respect to the number of joints. So occlusion is basically occlusion of the joints present in the scene. So here's maybe an example where his elbow joint might be occluded, right? So that's what we mean. But we don't consider the legs as part of the occlusion because it's actually out of the scene already. And so this is the progression then from easy to hard. And so we do a comparison now between the integral regression versus the heat map detection to see. And if you average all of the instances, so if I don't care about any of these sub-benchmarks, then what we observe here, and I do believe this is millimeter or pixel-wise EPE. If I'm correct, I think, yeah, this is the pixel-wise EPE. And on the left-hand side before the slash is going to be the heat map detection method, and on the right-hand side is integral regression. So these would be the standard numbers that all the papers report that you see in the results. You see that the heat map detection indeed has a lower error than our integral regression, right? But interestingly, if we now start to split these sub-benchmarks, for instance, by considering only the number of joints, what we observe then is that for certain ranges, the regression tends to do better. In this case, when very few joints are present, so this is the hardest setting, then regression does better. And similarly, if we consider the different resolutions, in the easiest setting, which is the highest resolution bounding box, then detection does better than regression. But in the other settings, regression seems to have a bit of an edge. And of course, if we now really break it down to the finest divisions, and then we pick the obvious cases of the difficult settings, so the lowest resolution and the fewest number of joints, or the greatest amount of occlusion and the fewest number of joints, etc. Indeed, integral regression has an edge. But on the easiest settings, heat map detection certainly seems to do better. And this was kind of an interesting result for us, which we hadn't observed in the literature at all, because everybody is only reporting this one last number here, right? So it has to do with the data set statistics. And once you divide it into these sub-benchmarks, then this phenomenon becomes clear, but otherwise it ends up being obscured by the overall statistics of the data set. And of course, the hard settings, you have much fewer samples than the easier. That's why it seems like heat map detection does better than integral regression. And so then we try to go back to go further and ask, well, you know what, our theory tells us that integral regression should be doing better all the time. But what we're observing is that this is only true in the hard cases, but not in the so-called easy cases. Why is that, right? And one phenomenon we observed was that actually there's a shrinkage in the density of the heat map. And we verified this in two ways. So here, basically, we're defining some area, defining or fixing S, right? This measure S that defines how large of an area that we're willing to consider for the heat map. And then we're going to sum up all of the activation inside. So, and what we observe is basically that as sorry, I've lost my train of thought here. I think there's a problem with this plot. Basically, that I think as you progressively sum up as you progressively get larger, for some fixed S, the summation of the regression is higher than the detection, which means that there's more activation within a fixed area, right? And the more activation there is, the more localized, right? You can argue this way. So this was our rationale behind this plot here. So yeah, that's why the regression is a bit higher. So for instance, within some, let's say 4x4 area, 60% of the activation is already contained within this local area for regression, but only 50 or 40% for the detection. Right. So this was our conclusion here, was that the integral regression's heat maps are more localized. And the other interesting thing was that if we were to fit a Gaussian distribution to these heat map densities and then compare the two, and you can compare the optimal sigma for the fitted Gaussian, what we also observe is that indeed regression, the sigmas are much smaller than for heat map detection. So these two are more or less confirming the same thing, that the heat maps for integral regression seems to be more localized than for heat map detection. On top of which, this is especially true once you progress to these easy and medium benchmarks. So on the very hard settings, regression and detection are both fairly dispersed. And then as you progressively get to these easier cases, the joints, because they're relatively easy, your likelihood is more concentrated, but for regression, it's much more concentrated than detection. So here, the Gaussian distribution is comparable on the hard cases, but for the medium and easy cases, it's more and more localized because you get smaller fitted sigmas. And then now the next conclusion that we observed was that actually, because this very localized heat map, so it's a shrinkage of the density, when you become too localized, this is what causes problems. And we observe this in two ways. One is for the detection-based methods, because we're constructing these heat maps, the ground truth heat maps, we can decide what sigma we want to use to create these Gaussian-based heat maps for supervision in the first place. And the standard is to use 2, sigma of 2, but we can, because we're constructing these ourselves, we can vary them ourselves also. And what we find is really that there's a sweet point of actually, so 2 is the standard and it's also the optimal setting. And if you make these heat maps for supervision any smaller or any bigger, you start to deteriorate in performance here. So here performance is measured by AP, so higher AP is better. And especially when you get to this very small sigma, it has very poor performance, a low AP. So this is for the detection setting. And for the integral regression setting, we do the opposite type of experiment where we enforce a regularizer to penalize very large heat map gradients. And what I mean here by heat map gradients is basically the delta between the neighboring pixels on the heat map. If we penalize these large differences, then presumably you will have a smoother or more dispersed heat map. When we add this regularization, we can improve the overall AP. We improve the overall AP and we improve the AP for the easy and the medium cases. For the hard, also a little bit. So what we're finding is basically that in both settings for both heat map detection and integral regression, when the heat map is too localized, this causes problems. Now, why is this problematic? This is our speculation at the moment, so we're happy also to get feedback on this point. We think, so actually this is not we think, this is given by MS Coco, that basically the ground truth annotations, because they ask multiple people to annotate specific joints, this follows a Gaussian distribution. So everybody marks it a little bit differently, right? And so we're going to model this with a Gaussian distribution, that the ground truth joints belong to some distribution, a normal distribution with some true mean, so the true location of the joint, and some sigma true. And if we also assume that our heat maps are Gaussian, so here are estimated heat maps, this J hat, then it's going to be based on, so the J hat is again some Gaussian distribution. Now it's centered at the same mu that we talked about before. And then the sigma hat is basically how dispersed or localized our heat map is. And what we think is that basically if this J hat is far from the ground truth joint, then it's beneficial, more beneficial for this sigma hat to be higher than the distribution of the original ground truth locations, right? And so one way of thinking about this is if you consider the very degenerate case, when sigma hat becomes very small, then there's no chance for your heat map, which is aligned at mu, to overlap with the ground truth, right? So if your location is perfectly correct, then having a small heat map or a large heat map doesn't have as much impact. So optimally, of course, is the two matches. But in the situation where your estimated joint does not align with the actual ground truth, then it's more beneficial to have this heat map to be more dispersed rather than localized, right? Next, we consider, well, why does this collapse or the shrinkage of the density occur? As I showed previously here, you see it shrinks a lot, especially for regression, but for detection, it also shrinks a bit depending on the case, but not as much, right? So why is this happening for regression, but not for detection? And so for heat map detection, what we realize is that this has to do with this direct supervision by the generated heat map. And the generated heat map has a fixed size sigma, right? So this is based on how we control the ground truth. It has nothing to do with whether it's easy or hard. We always use a heat map to supervise with some fixed sigma. And so you can see here, this is the loss for the heat map detection setting. This H is a Gaussian with some fixed sigma. And so it forces it to learn learn and produce heat maps that don't go any smaller than this fixed sigma that the ground truth was generated on. Whereas in regression, we are supervising directly with the joint coordinates, right? So we have no control over how the heat map, this internal heat or latent heat map that's being produced, we have no control over what it actually looks like. And then a second point that we discovered why it tends to shrink especially for regression is this presence of an induced bias. And this induced bias actually encourages very localized heat maps, or the density to be very small for integral regression. And this induced bias comes as a result of combining this expectation operation with the softmax normalization. So if you consider this 1D setting here that I'm showing, here you have a peak. And so this is also where your expectation would be in a true proper distribution, right? But because of the normalization step that we're doing with this softmax normalization, what ends up happening is that you end up pushing everything just a little bit above, right? So even the close to zero elements, they get pushed to a non-zero amount. And so then this essentially distorts your expectation, right? And so the difference between the actual peak of your heat map and the actual expected value is your bias. So here we're showing it in 1D. And to minimize this bias is when this bias ends up being more and more minimalized when your distribution here is more and more peaked, right? So it's more localized. So this is why in integral regression, it ends up learning very peaked distributions, is because it's trying to reduce this bias, right? So you can think of it this way: is the ground truth is telling you to estimate this location as the ground truth of the joint. But every time I do this expectation operation, I end up here, right? So you're always going to have this error. And we're trying to reduce the error between what the ground truth is telling me versus what the actual output is. The only way that I can do this and remove this bias is then, of course, to make this distribution as peaked as possible. And so this is what it looks like then in 2D. So here, this white square is the expectation. So this might be my overall heat map, my unnormalized heat map. If I take the expectation, this is where my actual output joint is going to be. So obviously, let's suppose that this heat map is even more or less correct, and your ground truth is over here, but your expectation operation at basically the final output of your joint is coming here. You need to basically try to reduce distance, right? And this, of course, is also controlled by the beta parameter in the softmax normalization. So if you have a very small beta, this is a large bias, but if you have a large beta, then this is less bias. So basically what this means here is that if I have a large beta, when I normalize this heat map, so here we're visualizing the unnormalized heat map, so maybe this is a bit hard to imagine. When I take a very large beta, then this distribution becomes extremely peaked in the normalization process. Then the expectation will be much closer. And so our solution to handle this bias is to choose the beta appropriately, and at the same time try to compensate for the bias. So here, this is the other thing, is that, but you can say, well, you know what, if this beta is very large, why don't we just choose a really, really large beta, and then this bias wouldn't exist, right? But then you run into difficulties for backpropagation. So in the extreme case, you can imagine if beta goes to infinity, then this softmax normalization basically becomes an argmax operation, right? And so you also don't no longer, it's no longer differentiable in that situation. So you cannot choose too large of a beta. So you want to choose a suitably sized beta, but still ensure that you can still backpropagate and that this operation remains differentiable. And to get a good chosen beta, of course, this is via experimentation. We try different settings and see what still works reasonably. And then the other setting is that we explicitly put in some compensation for the bias. And the way that our bias compensation works is basically to say, I'm going to partition the overall heat map into 4 quadrants. And then if we assume that your heat map density is perfectly centered here in whatever quadrant, because once the heat map itself is centered, then the expectation is no longer biased. Then we can remove the components of sigma 2, 3, and 4 here. Sorry, omega. And so we're going to remove the influence of these unactivated areas. And so through actually some simple linear algebra to do the manipulation, you can end up with this unbiased regression output. So this is the original output, which is taking expectation over the entire part. And then you can remove the portions of omega 2, 3, and 4 through this type of scaling and offset. And here the C itself is the overall normalization, this summation at the bottom. And what we can do then is basically, so you can already just directly use this bias compensated output and use this in the learning, like I showed on the previous slide, just directly use this in place of your original output, regression output. We go one step further and we say, well, you know what, because the training of the heat map detection actually gives a very good spatial distribution and prevents the collapse of the sigma, we still want to take advantage of this per pixel level of supervision. And so we introduce this joint loss here between the original, this regression loss with an offset, bias offset joint, as well as this detection, this per pixel supervision. And the per pixel supervision we give only at the beginning of the training. So here with this lambda function, when t reaches a certain point, then we turn this off and we focus only on the regression setting. If we compare this to different baselines, so here we're looking at on MS COCO on the validation set, then what we observe here, so these are 4 different baselines that we're looking at. So one is the integral regression baseline, and 3 others are detection, heat map detection methods as baselines. Once we convert them into a regression setting, so basically what we do is we remove this very last bit of the this argmax operation, and we instead insert the regression operation. Then you can see that basically the performance always drops a little bit. But if you use our method of compensating for the bias, but still maintaining some of the training from detection at the beginning with the spatial heat map, then we can improve upon the original baseline itself. If we compare to state of the art also, what we observe here is that basically our results were comparable to state of the art heat map detection methods. So here in terms of AP, we're all sitting at around the same, and then also in terms of the AR as well. So yeah, we're slightly lower than, for instance, UDP, but comparable to this dark method. If we look at the sub-benchmarks that I talked about earlier, what we notice is that basically we can improve definitely over the standard integral regression setting. And in some of these sub-benchmarks, we can also improve over the heat map detection, especially in these settings where it was otherwise easy, considered easy. So here, this D is for detection, R is for integral regression, and what we're showing here is the error on the y-axis. So lower is better. And so in this easy setting, for instance, where there's very little occlusion and all the joints are present, then regression does worse than detection. And in our, so S is our method, then we can actually push the error to be even lower than detection, right? Whereas in some of these harder settings, we can, we improve upon the detection, but we're not as good as regression still. So I didn't cover in today's talk, but this another phenomenon that we observe when we're comparing these methods is that actually the regression is much slower to converge than the heat map detection. And the reason for this, we think, is because the gradients are not as informative for the updating. So I didn't cover this in today's talk because it goes, there's quite a bit of lead up, so for time. So I would encourage you to have a look at our ICLR paper if you're interested in the details of this. Yeah, so that pretty much finishes off this first part of the talk about integral regression. Within my group, actually, so one of the areas we work on is pose estimation, both of the human body and of the hand. And another area that we also cover quite extensively is on activity recognition. Oh, sorry, before I continue on to the next part, I do want to acknowledge that. So what I presented here is work done by two of my students, Coarse and Lin, and the material we took from our ICCV paper as well as our more recent ICLR paper, and as well as some new material which we're still preparing here. Actually, Coarse is, I think, in the audience today also, so if you guys have other questions, you're also welcome to discuss. So yeah. For the last bit of the talk, I just want to show some other settings some other problems that we're working on in my group. And one of these cases is because we do work quite a bit on activity recognition, we're focused on this idea of developing applications for smart assistants. And so you can imagine in this setting here, you're wearing some AR or VR goggles of sorts. And you want to complete some task. And this task is maybe has multiple steps and is quite complex. So some examples are things like cooking or assembling some furniture or doing some plumbing and repair. Then it's an ideal setting where you can have some assistance to help guide you through whatever you're doing step by step, right? And so to model this problem, we introduced a new task or new setting of toy assembly. And so these are some toys, maybe there's about 10 to 20 parts or so you can see. And the objective is to put these together. So assemble these toys. And so you have each of the steps. And the nice part about this part is that there's different ways to assemble these toys, right? You don't have to follow a very strict order necessarily. Oh, so the video plays, this is good. So we recorded this data set, which we call Assembly 101. And it's a multi-view setting where there's both static cameras as well as egocentric cameras of the people. So 8 static cameras and 4 egocentric views. And we built this dedicated rig to do the recordings, and as well as this headset here. And so here are some stats, but basically we assembled 101 different toys over 50 some subjects, and we ended up with about 500 hours worth of videos. So there's 362 unique sequences, so of assembling and disassembling the toys. And these are the various categories of toys. So we were always looking at vehicles, and then we have various different shapes and sizes and colors of the toys over for different purposes. So some are construction vehicles, utility vehicles, or just everyday types of cars. And we try to select them so that, you know, they have some shared components, but also some unique components as well. So we've labeled this with different fine and coarse action labels. So this fine action is determined based on pre-contact, the interaction with that part, and then the post-contact. And a coarse action is basically related to one component here. So here, for example, detached bumper consists of these 5 different fine action labels. And to ensure that we get some sufficient ordering between these toys, we didn't give any instructions to our participants. We just gave them a picture of the final toy, and then they were free to put them together and, as they see fit. And so we get some very nice ordering variations to study this whole sequencing problem. And one really unique aspect of the data set which we observed was the fact that also people tend to make mistakes when they're assembling these toys, which was kind of neat. So then they would go back and fix the toys as well as fix basically they put together the parts in the wrong order, so they have to go back and fix it. So they detach some parts and then put it back together again. So in this example, for instance, this cabin, it cannot be attached before the interior. So if they try to attach the cabin already, then they have to go back, detach it, put in the interior, the seats before they can attach the cabin. And where we want to go with this, of course, is to be able to recognize the actions based on the specific hand poses. And so we, of course, also then annotated the poses as well here of the hands. So here we have the coarse action labels, the fine action labels, as well as the mistakes, as well as the 3D hand poses. So all of this data has been released already. So the paper will be released at CVPR this year, but the data is already available for download. So if this is relevant to anything that you guys are working on, I encourage you guys to have a look and check it out. And we are also featuring the data in 2 upcoming challenges at ECCV, one for doing the activity recognition and one for doing the hand pose estimation. Yeah, so that concludes what I have to share today, and I'm happy to take questions.